How to do linear static analysis in Abaqus? Hey, so we are going to solve this using Abaqus 3D in HyperMesh. So we are constraining it in this location and we are applying the load here. So everything we are going to do in Abaqus profile here. So before importing our mesh, what I have done is I have just created a solver interface as Abaqus standard 3D, and then I have meshed it using this cell component, this and this part, and this part is my solid component. So this cell is like here, it's of 1 mm thickness. So I'm going to assign the property here in Abaqus. So this property, this is anyway, which is whatever is cell section. I need to define the property in cell. So I can just put here 1 mm as name, and then I can just go on here and put as thickness as 1 mm, and then I can just go to here this cell and I can just go to this property and assign this as 1 mm. If you want to see whether it is applied or not, you just go to here this bar and just go to select this. You can see that 1 mm has been assigned to this. Now again I need to create one more property here for the solid section. So I'll just go on here and create instead of cell section, I need to put here a solid section for solid elements. And now I will just put here and call this solid section property. Okay, as property, this is property 1 which goes to solid steel. Okay, let me for time being change this name to aluminum. Just name changing the components, and then I need to define the materials now in this. So materials I am using this I'm will be following the consistent unit system in Abaqus. So basically every solver follows this consistent unit system. I need my length in mms, so and force in newtons. So by default I need to follow this ton second newton, this unit system. So based on that, I'm just going to define the material property as suppose as steel, for example, and then I will just need to define the density, which is 7.9 e power minus 9. By the way, this is in tons per mm cube, and elastic I need to define it as in uh, Newton per mm square. So this comes out to be 210 E3, and Poisson's ratio is anyway unitless, so it is 0.3. So this is for steel. For aluminum, I will just duplicate this and type aluminum, for example, and I will just change the density to 2.7 e power minus 9, and Young's modulus I can just put 70 e power 3. That's fine. Now I'm just going to the properties and cell. I want the cell in my steel. So just select this steel and this property solid section I want as aluminum. I'll just go on to aluminum. So just change the colors, and if you see here, this is aluminum and this color is steel. That is fine. Now in Abaqus, there are two ways to constrain this. Basically, we can constrain on sets or we can constrain on directly on node numbers, but constrained on set is mostly preferred. So I'll just create two sets here. So the whatever the set which you want to have nodes is called as n set in Abaqus. So just I'll type here as fix suppose, and I will need to constrain this by h, and this is fine. So you can just review this by pressing the button Q in the fix. by selecting the fix. So these are the nodes in fix. Now for applying the force, I will just put here load, and I'll just clear this nodes from the load, and just this nodes I need it. So this nodes are done. Now I need to create one load collector here in Abaqus, and I can just put here, I don't want to give any initial condition. This is a linear static solution we are doing. So linear initial condition will be always be mostly in a stress-free condition, we can say. So I'll just put here as history, and uh, I'll just activate this, and now I can just go to here analyze, and just go to this constraint, and instead of this set I can choose at fix. That's okay. And all DOF I will just put as constraint, and I'll just close this. So to see this whether this is applied or not, you can just press Q in the load collector. It will showcase that this is constraint. Now I need to apply the load also. So load also I can apply in set. So load set I will just put here, and magnitude I need in in this y direction. So I'll put here as 1 and here as 0, and I want at every node I want as suppose minus 0.01. If you see here, if you see press Q, this load has been applied to this in this direction to negative y of 0.01 C load. Okay, this is fine. Okay, let's instead of 0.01, let us increase this load. So you can just go on here and put minus 0.1. That's it. So load has been increased to zero point 0.1 in these nodes. So total, if you say what is the total load applied, we have applied the load and set contains 9 nodes. So 9 into zero point 0.9 Newton load we have applied. We are applying it here, and we are constraining it here. Now I need to create one load step. So load step is created, and we can just put here the name of the load step, suppose linear static I can say, and this load collector, I want this load collector, and analysis step is static, but by default Abaqus will always choose the static nonlinear. To make it linear, uh, there is a thing called as perturbation. So perturbation means the response we want to consider is linear. That means that stiffness matrix is a stiffness matrix doesn't change from 0% of load to the 100% of load, and it doesn't depend on the displacement. So I need to find this perturbation. So if you click this step parameter, just click on this perturbation. That's it. Now output blocks I need to create. So I need stress and displacement. So output block I will create, and these all are in file format. I want in ODB, so I can just go to here, output here, and this uh, field output is default. Let it be default, and everything let it be default for the time being. We can discuss it later. Then displacement comes under node output. So you just click on here and let it be 1 here and just type U. That's it. U is nothing but the symbol for displacement. For element output, just click on element output. Don't check anything, any other box. For the time being, we will discuss this later. What is this? Just put here S. That's it. And then I will just call this output block again in my load collector card. Sorry, in my step collector card. So just go on here and select this output card. So this is done. By the way, the deck setup is done. But one thing we forgot to do here is, if you see here, there is no connectivity between this solid to this cell and this solid to this cell. So how to do it? So we can use various ways to connect it. We can define interaction, we can define tie contact. But for this analysis, what I can do here is I can just create one-to-one rigits here. So to create one-to-one rigid, just go to this create and new and just make sure this is created as rigid, and this should be more than your gap, this gap. So I'll just go to the here this elements. You just unselect these elements and just do this, and one-to-one rigits have been created. Similarly, I can just go here and okay, and just go here and do this. So this one-to-one rigits have been connected, you can see here. And by the way, you can just check this. This dependent def should be 1 2 3 4 5 6. Once this is done, this is done here. And you can, if you want it, you can just delete this connectors, and your connectors are deleted, but your FE is same. Means FE information is relevant here. So I think we are ready here, and we can just export this deck. So this, replace this, and just I don't want any comments here. I'll just go on to export this. Okay, just, and then I will just open this for you to see what is happening, what has happened from the HyperMesh to this. So later in the video, we are going to text edit this also. So star node, whatever is double star, Abaqus doesn't read those comments. Those are treated as comments. So even if I delete this, nothing is going to uh, happen if I delete the double star things. So double star is nothing but comments. Single star means some uh, some command is there. So star node, and it is followed by your node number and your coordinate in X, Y, and Z. So once this node number is done, you can see this uh, Abaqus defines some element type. So S3 is nothing but your trie elements. So whatever trie elements comes under cell 1, it is defined like this. And whatever the quad element is defined by S4, whatever quad element present in this, it is defined by this. Similarly, whatever this is some C3D6 is penta element. So this penta elements and EL set has been defined like this. And if I just choose here mat, so whatever kinematic coupling means this RB2, whatever we have created it here, it is defined like this. So this is your independent node, this is your dependent node, and this 1 to 6 LDUFs. So whatever we have done in HyperMesh, it has exported like this in this format. And star cell section means the thickness assignment, material assignment it has done. Cell section, whatever comes after this, it is 1 mm. So we have given 1 mm thickness and it is replicating here also. So and set has been defined. Material name is steel and material properties also it will define. And then if you see here from here, this has defined your load case and whatever the outputs you wanted. So these are very end in the abacus. So star step perturbation, star static means this is linear static. Star boundary is nothing but your SPCs. Star load is nothing but your loadings. And star output field is your output field. Once this is done, we can now solve these things. So I'll just delete this things and just I'll type as CMD abacus J is equal to this file name I need to type ss1 and int means interactive. So there are three ways to see how your run has completed. It means if this message is coming as completed, that means your job is completed without any errors. You can just go on here to that file, and that file, if you search, if there are no errors, that means your job has passed the syntax check. And this contains other informations also we will see, and it should say your analysis has been completed. Then you can just see the results. Just type this ODV and in the input I can just put here INP and just I will put this feature and see. So it is reflecting whatever we how we are wanting it. And by the way, this displacement is like this. We are anyway we were applying the load, so maximum displacement is going to be like here because we are fixing it here, so it is treating like a cantilever, and your stresses should be finding out somewhere here. So your max stress is somewhere here. So this is how you can put linear static in Abaqus. By the way, why it is uh, almost zero stress here? The reason being entire this is kind of it is bending from here, and whatever here this is very stiff for deformation because a lot of uh, it is kind of a sandwich kind of a structure. So this is how you can perform the linear static simulation in Abaqus using HyperMesh as a pre and post processor, and you can download the INP file from the attachment. So yeah, this is one of the videos. Thank you. Have a great day.